Okay, I'm going to get things underway. So, I'd like to acknowledge the traditional owners of the lands on which we're meeting today, the Wurundjeri people of the Kulin Nations, and offer my respects to elders past, present, and future. Okay, that was a bit better than yesterday. So we have Rich Shiffrin to talk to us again today. Very interesting talk yesterday, and this is on an entirely different topic. So Rich is very well known for his memory work, but he's also always been interested, well, in puzzles of all kinds, but in particular paradoxes. And today he's going to regale us with all the things we don't know about regression. Thanks.
Okay, this is a talk that I prepared a few months ago, and there's about 6 different closely related threads that led me to produce this, as I hope to make clear as I go through this talk. I decided to produce this originally for a reason having to do with teaching statistics, and then it turns out that it's very related to several other things I've been working on for the last several years, including a conference I'm running next summer. I'll mention this later. I better see with my slides myself. So what happened was that led me to this was a teacher of undergraduate statistics, a PhD student of Rob Goldstone's, had gotten to a university in Los Angeles, an undergraduate institution, and was teaching statistics. And she was worried, as Rob Hoffman Goldstone was, that maybe the students were just memorizing formulas and didn't understand what they were doing. So she decided that a good way to help them understand was to teach them the use of R to program regressions, and did that. The students some of them seemed to like it, not so much because they understood statistics, as it turns out, but they enjoyed learning to use R. But in any event, the idea that teaching them to program regressions would help them understand statistics struck me as a little strange, because I had spent a number of years now trying to understand regression myself with not entire success. And therefore, I thought it was sort of funny that you could teach people to program regressions to try to make them understand statistics, when it was turned out that not only I, but statisticians and causal theorists have been puzzling over these issues related to regression for many years. And there's a variety of educational questions that we want to ask, which is, if it's hard to understand something as simple as regression, what level of understanding do we hope to impart to our students, and so on. I'll get to this later. So there's a lot of different types of regression. Some of them can be very complicated. You can have Gaussian process regression. You can have multidimensional regression in various forms. But even the simplest kind of regression is a little complicated to understand. So let's simplify enormously to simple linear regression with one independent and one dependent variable and Gaussian noise, which is the thing we usually see. So as an example, what you might have an equation fit the data, the red dots, where the equation is a linear function plus Gaussian noise. Okay, what could be simpler? This is a pretty trivial example of a regression. So it's hard to imagine anything could be hard to understand about this, right? Well, there's a couple of things we'd like to understand when we see when we're summarizing data with a regression. We'd like to predict in the future what we would expect if we have another value of X on the horizontal axis. What will we predict we'd see at the Y, on the Y value? That can be somewhat complicated due to technical issues, as I'll describe. And then the more fundamental and difficult issue is interpreting the data that are summarized by a regression. So the regression is a way of summarizing noisy data, and how do we interpret it? And this turns out to be a matter of scientific induction, which is a hard process, a hard problem. And I believe that much of what I'm going to be talking about that's been puzzling statisticians and causal theorists is due to the fact that they're attempting to figure out a way to do induction with deduction, which is impossible in my estimation. Let's give some examples of regressions. So here we have red dots given a treatment, blue dots that aren't given the treatment, and we summarize the data with two regressions, one for each set of subjects. And you might think that the treatment had an effect equal to the difference between the regressions. In the lower example, I didn't draw the regression lines, but you can imagine the same regression lines applied to the red dots given the treatment and the green dots not given a treatment. They don't exactly lie on top of each other anymore, but you might assume there was no difference. But suppose the treated people were men and the non-treated people were women. Then the differences or the lack of a difference could be due to gender and not the treatment. Well, it seems you wouldn't want to do that. Well, we're going to see that that's a confusion that is going to exist many times in what I'm going to be describing to you. We'll see how that works. Okay, it seems like it's a strong statement that if you want to compare two individuals at the same value of X, they better be equivalent individuals. So if you want to compare treatment versus non-treatment, the people given the treatment ought to be as equal as possible in all ways to the ones not given the treatment, other than the treatment. So you can unambiguously assume that the effect of the treatment is due to that and not due to some difference in the individuals in the two groups. Well, I wish people would notice that. Okay, well, I'm going to start by describing some of the difficult things to understand with regression to the mean. Now, this was first analyzed and explained well by Galton in the 1880s, when he noticed that, for example, children tended to be shorter than their parents, and parents tended to be shorter than their children. That is, there was always a regression to the mean in height. That is, there was a tendency for both groups to be less extreme than their either parents or offspring. And he figured out how this would work with regression to the mean. I'm going to use an example, which I'm going to go back to later, from Lord's paradox. I'll explain later what happened. This was a figure that was used by Frederick Lord, a well-known and very good statistician working for the Educational Testing Service. And this is from a publication, a two-page publication that he put in Psych Bulletin in 1967. But all I'm going to talk about now, I'm not going to talk about Lord's paradox. We'll come back to that. Just take a look at, what this is representing is that on the x-axis are the weight of boys and girls when they arrive at school, measured on some scale. And then on the vertical axis are the weights at the end of the semester when they're weighed again. And the Gaussian distributions you see on the top show the Gaussian distributions of the girls' weights and the boys' weight initially. And on the left axis, we have identical Gaussian distributions representing the weights at the end of the semester. And let's just focus for now. And the regression lines shown are the correctly plotted regression lines for the joint data. And we can imagine that each individual has a point on the horizontal axis representing their initial weight, a point on the vertical axis representing their final weight. There's a joint distribution in the center of the plot representing all of the joint values for each individual. And they're represented by a ellipse showing the, say, one standard deviation of the joint distribution for the boys and for the girls. So is that all pretty clear? Okay, let's just focus on the girls for the moment. So let's take a look at a very light girl, which would be where the orange bar is, okay? And if you look at the joint distribution, where the orange bar is for that very light girl, you see that most of the points are above the diagonal line, representing equal weight of initial and final. Okay. And what this means is that the light girls are now in this plot, in this hypothetical data, are mostly gaining weight. Okay. If I move that light orange bar over to the right, so we're looking at a very heavy girl, the opposite is true. Now we see that if you have a heavy girl, given initial heavy measurement of initially heavy weight, you're going to see that they tend to lose weight, according to this data. Okay, so even though all of the initial, maybe the distribution of initial data and final data is identical, as for the group, we see that there's a tendency for the light people to gain weight and the heavy people to lose weight within each group. And Galton explained this as regression to the mean. So you can think of this the following way. In the what's going on is that the girls' initial and final weight have two components. Let's imagine there's a stable, let's imagine there's a mean that each girl has that they're fluctuating around as a simple model. So that over time, you have a fluctuating, a sample from a Gaussian distribution of a girl's weight. And that the initial weight at the beginning of the semester is a sample from that distribution with the fixed mean. And at the end of the semester is another sample, independent sample, because it's far away in time, another independent sample from that same distribution with the same mean. Okay, so we have two samples from a Gaussian distribution are being made. And we can imagine that the weight itself is two components. It's one component is what does the mean for that girl from the distribution of all girls? And the second component is a random sample from a Gaussian distribution. Okay? And the idea is that when you have a light girl, let's say where the orange bar is, that tends to be it tends to be a light girl, probably, but it also, if you had to infer, but also it tends to be a light sample from that girl's Gaussian distribution. That is just two components to lead you to an unusually light measurement. One of which is a light girl and the other is a light sample, usually less than the mean, let's say. And what do you expect then for the next sample for that same girl? You expect it to be at the mean, which means that if this is an unusually light sample taken from the Gaussian distribution, the next one tends to be at the mean, so you expect it to be bigger. Similarly, if you had a heavy girl, the opposite happens. You'd expect that to be, one component would be a heavy sample from the girl's distribution, and you would expect the next sample to be near the mean, which would be lighter on the average. So this is all matter what Galton would say, a regression to the mean. You would explain this set of data very simply as simply two independent samples taken from each girl's own distribution of weight. It would be one way to explain this data. So that's regression to the mean. Maybe if this is at all confusing, think of just taking two successive samples from a Gaussian distribution with a known mean and some fixed variance. The second sample is going to, on average, be closer to the mean than the first. We say on the average. And the first will, on average, be closer to the mean than the second. The key here is what you mean by average. On the average, you're going to be at the mean. But the sample you take is going to be away from the mean, of course, with probability 1. So whatever the sample is, that in whatever direction away from the mean is the sample, on average, the next one's going to be at the mean, which is going to be regressing toward the mean. So there's a regression to the mean in a trivial way. Okay, maybe this seems obvious, maybe. The regression lines that I show here, which are correct regression lines, are reflecting what is the best mean square prediction for a given initial weight, and is reflecting the model that I mentioned, which is based on regression to the mean. That is, they show correctly, these regression lines, that the heavy girls lose weight and the light girls gain weight. So it's correctly representing the predictions that you would make on the basis of initial weight. Of course, there's another regression line, which is different that Galton pointed out, which is if you regress the initial weight on the final weight, you get a different regression line pointing in a different direction because the opposite happens. And it's just what I said about sampling from a Gaussian twice, that whichever one you focus on, the other one is going to be regressing toward the mean. This is Galton's 1885 description of what's going on in regression to the mean. And I won't try to interpret this to save time. The idea that there's two different regression lines, so depending on which you think of as the controlling variable, will be important later on if we turn to Stein's paradox, which we'll get to later. Is it always the case that we would get regression to the mean every time you see a regression? Well, no. Let's say we're measuring the weights of barbells instead of people, and we don't expect their weights to vary. So we have barbell sizes along the x-axis, and we're going to measure the weights with a noisy scale. And we might get a joint distribution with the standard deviations shown with the orange lines, and with the mean shown as the regression line, shown as the blue line. And we expect that the best prediction for any barbell size would be the blue line mean, and with some variability shown in the plot. Well, we don't expect regression to the mean in this case. The barbell's weights are not expected to change, and we don't expect any regression to the mean in this simple case. Let's consider the following kind of noisy data that's ellipsoidal in shape, like the one I showed for Lord's paradox. But let's say that as opposed to the situation I showed you with the original plot, the regression line through the ellipsoidal data lies directly on the diagonal. Let's imagine. So that as opposed to the regression line I showed you earlier, which was tipped with respect to the no change diagonal, this regression line is exactly on the no change diagonal. What might that mean? Well, you might say no regression to the mean is operating, but it turns out that could be very hard to justify with an actual model of how the data were generated. I mean, obviously the joint distribution is showing this variation in the final weight. If there's variation in the final weight, then you'd expect variation in the initial weight. And if there was variation in the initial weight, then you'd expect regression to the mean. If so, then you might expect what's really going on is that the actual data of the true weight might be represented by the red line below, where the heavier people are actually heavier at the final weight. And regression to the mean is operating. So the reason you end up with a regression along the diagonal is that you are having regression to the mean, which is moving the heavy people down to be on the no-weight diagonal and the light people up to be on the no-weight diagonal. That also seems like an unlikely model. The point is that if you had this ellipsoidal joint distribution with a regression line on the diagonal, it's hard to come up with any model that makes sense scientifically. And we're talking about induction now, figuring out what the regression line means, not deduction. And so the regression line might tell you your best prediction for any given initial weight, but trying to justify how the data could come about can be very hard. Okay. And a different model that could explain regression line on the diagonal would say that all the girls end the semester at the same weight as the start, but that the scale used at the start was accurate, and the scale used at the end was inaccurate with a correct mean but a high variance. That would produce the data, but again, that seems like a very strange model. Why would you ever assume that you're using a correct scale at the beginning and a noisy scale at the end? I mean, that's not a very good causal account. Okay, so I just think it's hard to explain data like that if we ever saw it. Suppose the joint distribution was exactly as shown here, but the actual scale on the left-hand side is 10 pounds up. So that what is actually happening is everybody seems to be getting 10 pounds. Okay, we still have regression to the mean now if we had this same data, except the left scale is 10 pounds heavier. Now you would argue that, I would argue for a model in which everybody on average gains 10 pounds during the semester. And the regression lines show correctly regression to the mean relative to the 10-pound gain. That is, the heavy girls gain less than the 10 pounds and the light girls gain more than the 10 pounds. And the same would be true for boys. So I'd argue that would be a reasonable model to explain data like this. Or you might have an even more complicated model where the whole distribution is shifted relative to the no change diagonal. So it's 10 pounds heavier plus a shift in the orientation of the regression of the no change of the orthogonal line, not the regression line, through the joint distribution. And then again, I'd just say regression to the mean is probably going on, but relative to the linear trend that is represented by the new data. Okay, hopefully you're getting a little confused by all this. This is not trivial, but it's simply pointing out what happens with regression to the mean that ought to be present in many of these situations with regressions. People get this wrong all the time. People have been making mistakes about regression to the mean since the 1800s to the present day. It's easy to make mistakes. And if you're at all confused about any of this, it's why people make mistakes. It's not trivial. Okay. I could go on and on and on talking about regression to the mean and problems associated with it, but I'll just turn briefly to Simpson's paradox. I'm not going to spend much time on it. Many of you have heard an example of the Berkeley admissions paradox, Simpson's paradox, where it turns out that each department is accepting a higher proportion of women than men. But because you're mixing different things with different proportions with different probabilities, all of Berkeley is showing that you're admitting a higher proportion of men than women, even though every department is admitting more women than men, or a higher proportion of women than men. It's not worth taking the time to go through the math here. I've heard people give long talks, an hour-long talks on all the different examples of Simpson's paradox and all the problems that causes and the problem and the many ways that people get this wrong. Here's a pictorial example of with regressions of Simpson's paradox in a slightly different way. So we can see that if we look at the two subgroups given by blue and red individuals, the regressions are showing a positive slope. But if you look at them together and draw a regression line through all the data, it's got a negative slope. There's another example of Simpson's paradox, depending on the scale at which you're analyzing the data. And of course, things can get much more complicated than that. Here's an example where at the smallest scale, the slope of the data is negative, the little lines. If you then analyze that group of three, it's a positive slope. But if you analyze all the data, it's back down to a negative slope. Okay. You can have a lot of examples of different kinds of regressions like this mixed together. We're talking about the difficulty of trying to interpret regression data when they're mixtures of different kinds of groups with different properties. And even worse is that the individual regressions may be subject to regression to the mean, and we've been mixing them in different proportions and different probabilities. You can imagine that this would be incredibly difficult to try to understand what's actually going on. Well, I've heard talks on Simpson's paradox that go on for an hour themselves. I'm not going to dwell on it. I want to move on and move back to Lord's paradox, because this indicates something I've been working on recently. The conference I'm running next summer is titled Scientific Inference and Statistical Inference, which is related to the difference between induction and deduction. And that comes up in Lord's paradox. So let me go back to this figure. Okay, the setup in this two-page paper, which was titled by Lord, A Paradox in the Interpretation of Group Comparisons. So statistician one had the model in mind that I described to you, that nothing's happening to the weights of girls and boys other than random fluctuation in their weights. That was the model I suggested, explaining the data. And that could be true of both boys and girls. To explain this joint data, where nothing really changed. The distributions at the end were the same as the distributions at the beginning. It looked like just random fluctuations are going on. Statistician 2 uses an analysis of covariance in ANCOVA, which amounts to interpreting the two regression lines that are shown. And the statistician concludes that both groups are gaining weight, but the boys are gaining more. And why would they conclude that? Well, it's based on the regression lines, the fact that the intercepts are above 0, and that the regression line for boys is higher than the regression line for girls. And that indicates that the boys are getting more than the girls. If you, for example, look at where the orange bar is, which is a girl and a boy of equal weight, you see that what we're really doing is measuring a heavy girl and a light boy. And naturally, in that case, since the light boys are gaining weight and the heavy girls are losing weight, or regression to the mean, it's not surprising that when you compare the two, if they start with an equal weight, that the boy is gaining more on the average than the girls. And if you look at where the vertical line is, you see most of the boys are above the diagonal, most of the girls are below the diagonal at that orange light. So if you compare a light girl to a heavy boy, you can see a justification for the conclusion of statistician 2, that the boys are gaining more weight than the girls. Both are gaining weight. Does that make any sense? Well, it doesn't make any sense if you believe the simple model I described that Lord had in mind. Why would you want to compare a light girl, a heavy girl to a light boy? Is that a proper comparison? That would seem, but it's a comparison that a number of statisticians think is reasonable. Well, when Lord published his 67 paper, he thought that he just used the word paradox as a ironic term. He didn't really mean it was a paradox. So that, but when people looked at his 67 paper, they thought statistician 2 might be reasonable. That conclusion could possibly be reasonable and thought it was a paradox. So he took another 2-page paper he wrote in Psych Bulletin to follow up the first one in 69. And in there, he made a note that the use of ANCOVA, in 67, he used the illustrative example of the figure I showed you to show how the use of ANCOVA can lead to absurd conclusions. So he didn't really mean that it was a paradox. He was just using it as an example of how silly it was to use an ANCOVA analysis for an example like this when it was so obvious that nothing was happening. So he posed as a controversy, an argument between statistician 1 and 2, but he meant it as an example where it was ridiculous to, do statistician 2. Well, Lord didn't think it was a paradox. I don't think so. Galton wouldn't have thought so. We all think of regression to the mean was explaining that joint data. Well, now we enter the twilight zone. Since 1969, there's been publications about Lord's paradox every few years by the best statisticians and causal theorists in the world. We have Box in 75, Cox and McCullough in 82, Howland and Rubin in 83, Winger and Brown in 2007, on and on and on and on. Every one of whom is giving reasons why statistician 2 might be correct. Well, do any of you think so? I found it a little bizarre. One of the things they do is point out, one of the arguments is that the two groups as a whole don't gain or lose weight, which is shown by the equal distributions at the end, but that the effect on an individual is to gain weight. Well, I don't really understand why, because in each group, the boys that are heavy lose weight, and the boys that are light gain weight, and the girls that are heavy lose weight, and girls that are light gain weight, and they exactly balance, is what's shown in the figure. I don't understand why they reached this conclusion. It doesn't make any sense to me in terms of developing a model. So it seems a little crazy. I should say that every one of these papers, these are long and technical papers, every one of which tries to argue that in principle, you can come up with some kind of a story that would justify the boys getting weight more than the girls and both gaining weight. Well, none of them actually produce a plausible model. Every one of these papers simply says in principle, this could happen, but they don't actually show you a way to generate the data with any plausible model that could do it. So we have these long technical papers, but they don't actually come up with a plausible model that a scientist would want to see that could have generated the data that Lord presented in his figure. There's a number of these papers are claiming that the causal question about what's happening, in other words, the induction question, what could have generated the data, can't be answered due to assumptions that need to be specified to remove ambiguity. So Rubin and Pearl and others have pointed this out, that we can't really answer the question because, and so on and so on. Judeo-Pearl actually goes a lot further. He not only gives causal diagrams and argues that only statistician 2 could be correct, and that the model that I was talking about and the one that Galton would prefer and the Lord preferred and that I prefer couldn't even be right. I found his arguments to be ridiculous, and I don't want to try to defend them. Well, is it necessary to specify assumptions? Well, of course it is if you want to do deduction. If you want to do induction and come up with a good model to explain the data that's shown in Lord's figure, it would be nice to be able not to use common sense and good judgment about what's a good model. It would be nice to be able to form deduction from the data. And if you specify enough assumptions and with enough rigor and enough specificity, you might be able to turn induction into deduction. But I don't think that's possible in general. And of course, the statisticians and the causal theorists would like to turn induction into deduction, but that's not science. I mean, it's impossible. Or at least I don't believe it's possible. Okay. Okay. I think all inductions of causality are a matter of coming up with a good story. What's a good model? Whether it's a quantitative model or just a verbally stated model, it's what scientists do is judge whether the story we're telling is a good one. And I can't imagine a formula that would allow us to do deduction to figure out what's really happening as best accounts for data we see. It's a matter of good scientific judgment. What leads the statisticians and causal theorists to reach this conclusion that statistician 2 might be correct? Well, I've suggested an answer, but I think this is a good example of the difference between scientific inference involving induction and statistical inference involving deduction. But regardless of what's going on and why these various statisticians and causal theorists have concluded what I find bizarre, the fact that so many leading researchers, statisticians, causal theorists, have found Lord's paradox real should give pause when believing that inference from regression is easy to understand. I think we can all agree that regression is hard to understand. Interpreting regression isn't easy. I don't know, maybe you agree, maybe you don't. Maybe some of you think you understand all this clearly. I'm trying to confuse you all. Because it's confusing to me. If you put aside all these induction issues aside and just talk about the deduction, can we at least say that we can predict what the final weight is based on these regression lines? So forget about the model that explains the generation of this data. Can we just use these regression lines to predict the final weight based on the initial weight? So you normally say, okay, we just find an initial weight for either group on the bottom. We look up within that group for the regression line, and that predicts the final weight. Well, sort of. Now we enter Alice in Wonderland and we go down the rabbit hole. Because actually, it doesn't quite work that way always. If we're predicting for a given girl within a given initial weight, what our best guess is about their final weight, it's the regression line. If we want to predict all of the girls, we better do a regression. And that regression can be either a regression to all of their weights, their mean of everybody, or a regression to 0. And then we do better at predicting all of their weights. What? That seems a little crazy, and I'll get to that in a minute. And this has puzzled statisticians for a long time, ever since Stein showed this to be true. What is Stein's paradox? It's a little hard to, it's easy to describe what it is, but it's a little hard to understand why it works. There's a math that's easy to follow that explains why Stein's paradox works, and everybody is very happy with the math. But people have tried for many years to write a description of what's happening that would be understandable without using the math, and no one seems to have succeeded in doing that I can tell. What is the result? Well, let me give you the most funny sounding version. Suppose you're taking several noisy measurements of a quantity because you want to get the average value of the quantity. So for example, let's say you want to measure the number of apples produced by a farm in Washington. So you take several measurements over several years, and you say on average, we would predict that the best account of the mean number of apples produced by the farm should be the average of the sample. That would produce the best least squared prediction based on the errors. Yeah, take the sample average as your best guess, knowing nothing else. Makes sense. Now, suppose you do this for several unrelated quantities. So we make another set of measurements about temperatures at a weather station in Vermont. We take the average to best predict what those temperatures are. And then you make a third measurement of weightlifting performances by a person in Georgia. And again, you would predict the best estimate of their weightlifting performance would be the average of the sample. Okay. This is a little different than the situation with regression to the mean, because in regression to the mean, the quantities are related. So then there's a mean to regress to. Here, these are unrelated things, so there's not clear, there's no mean to regress to here, it makes any sense. Anyways, we do this. I estimate all these unrelated quantities. Now, the funny thing is that if we want to make a best prediction for all of them, not just one at a time, we can do better than using the sample average. And what better means is that we shrink the estimates below the actual average of the sample. Now, this is a little crazy. There's several kinds of estimators that do better. Two that are famous are the Shiffrin-Morris estimator, which shrinks all these unrelated sample means toward the grand mean of them all. Why in the world should you take these unrelated quantities and shrink the estimator toward the mean of these unrelated things? But it works better. Or another is the James Stein estimator, where you shrink the sample means towards 0, which seems quite different than shrinking toward the grand mean of all the quantities, but both produce better mean square deviation predictions than the original sample means themselves, if you want to predict all of the quantities. Does this make any sense to anybody? Does this make intuitive sense? Why in the world should this happen? Well, the math shows it does happen, and then empirical examples have been worked out to show it actually works, it's true. And there's various attempts to explain why. I don't find any of them very convincing. Some of them talk about empirical Bayesian inference, and others point out bias trading off with variance. And Steve Stigler, historian of statistics, has a nice article showing how Galton's ideas of regression to the mean can explain this bizarre result. He was arguing that the regular estimator of the sample average, it lies on the line theta equals x, where theta is the unknown mean and x is the sample average. But he's pointing out that we don't, when we're predicting all of these things, we don't want the expectation of the sample average is given the unknown mean, because we don't know the unknown mean. We really want the expectation of the unknown mean given the sample average, and that's a different regression line. And he finds this as a good explanation for what's going on. I don't find any of these explanations that I've read particularly useful for intuition, but this is an example of trying to explain Stein's paradox with a reference to regression. Now, Stein is most paradoxical when it's applied to unrelated measurements, when we're shrinking these estimates and all the things we're measuring are unrelated. But of course, they apply equally well to related things, so that if we were using the regression lines to make predictions for the cases I'm talking about where all of the measurements are of the same thing, but have different values of the same thing, then again, if we're predicting everything, if we're predicting all of the quantities rather than just one at a time, we should be shrinking our estimates below the regression line, either toward the mean of everything or toward zero. Well, do any of you find this easy to understand? Raise your hand. I don't find it very easy to understand. And this is just deduction, as it turns out. We're just talking here about math. We're just talking about difficult to understand, intuitively difficult to understand math, not induction, which is coming up with an explanation of the best way to account for data. Again, there's long technical articles that by different people, all trying to explain Stein's paradox in a way that somebody will be able to intuit. None of them seem to work. I think what we conclude is that regression is hard to understand. Regression to the mean. I would say that understanding regression isn't too easy. And it's hard to understand how to use regression for prediction. It's even harder to understand how to draw conclusions from any given set of regressions. That is, we can summarize a set of data with regressions, but how to understand how interpret what generated the data is a matter of induction, coming up with a good model. That's even more difficult. And I don't want to leave induction to statisticians or causal theorists. They want to turn induction into deduction. And that's what the many articles that have been written about Lord's paradox ever since have been trying to do. They're trying to figure out a way to draw causal inference from data. But really what we need as a scientist is to come up with a good story. We want to come up with a good story that we find plausible as a way of generating the data. And I don't think we can do that by formula that's applied to the data we see. Okay, so maybe I've confused you a little. Maybe you all thought you understood regression. It's pretty simple, right? Well, I think understanding is a bit of an illusion. This is a pretty difficult subject, as I've tried to indicate with these various paradoxes, where the very best statisticians and causal theorists in the world have been having trouble dealing with this. So it's not easy. But that brings us back to the educational implications. Many of you either do or will be teaching statistics. This raises the question, if it's the case that most people and most scientists, even most statisticians and causal theorists, don't understand all of what I just said, and let's assume that a few people might not understand any of it. But if we're teaching statistics, then what do we want to impart? What level of understanding is achievable by what proportion of students? What level of understanding should we aim for? We can't aim for everything. Nobody can understand all of this probably. Is partial understanding good enough? And how should a given degree of understanding be taught? And how long can you expect anybody who does gain a certain level of understanding, how long can you expect them to retain it? And of course, these questions about understanding go well beyond the teaching of statistics. They're fundamental to any question about education, which is what level of understanding do we expect to get through? And what should we aim for? This is an example in statistics where I don't think we can aim for everything. We can't possibly expect the students we're teaching to understand all the things I just told you about regression. And what should we aim for then? What's an appropriate level of understanding? And is a partial level okay? Is understanding a little bit better than nothing? I guess I think that's the end. So anyway, I will be happy to entertain questions here. The hope I've had is that I've confused you. And the idea here is to point out that maybe it's not so easy to understand some of these things, even if it seems obvious at first. Thank you.
Thanks, Rich. So does anyone have any questions?
Yeah.
Your talk really, sorry, my friend just all right. Is it working now? Okay. Yeah, your talk really raised a question for me in my mind, what understanding is.
Yeah.
Actually, from a psychological point of view, can you give us some understanding about what understanding is?
I think there's two different levels of understanding we talk about here in the case of statistics. One is trying to understand deduction. That is drawing correct inferences logically and mathematically from a set of assumptions. And if you specify the assumptions well enough, then you can carry out deduction, but that can be very hard. In the case of Stein's paradox, it's extremely difficult, and everyone was very surprised when Stein first published his results. It's just deduction, it's just math, but it still surprised everybody because it didn't seem to make any sense. So that's hard enough. That's one level of understanding. The even harder level of understanding is induction. Because there it's a matter of what's the best account. There's no answer to this. It's what's the best account of that might generate a set of observed data based on your understanding of the current situation and the task and the data from it, and everything you know from history of a prior experimentation, what you believe is true of people and or the physics of the world. That's a matter of good scientific judgment based on everything you know. And there, we don't have a good account because nobody really ever agrees on what it is, what's the best model. Some people, different people have different judgments about what's a good model. Of course, we all tend to favor our own model. That's hardly a good way to judge things. We have a natural tendency to favor our own models. But if we have, quote, somewhat neutral parties judging the worth of models, eventually, truth sort of wins out a little bit. It's not that any models are true. Every model we use in every field of science is wrong in detail, whether we're talking about physics or psychology or cognitive science or anything else. But the models are useful often, and they lead to further progress. But what makes a good model then is not that it's correct. It's not our judgment that the model is correct, but that it's useful, that it does a good job, that it summarizes things in a simple way, that it does things in a way that we can understand because we want to communicate. If science is going to move forward, one of the most important things is that the model we produce that explains the data can be explained to other people. Because if scientists are going to make any progress, they better understand the model. And if you produce a model, you better be able to explain it, how it operates and so on. So that's an important factor. So anyways, the problem of induction is a difficult one. And that's a second level of understanding, which is even more difficult than the understanding deduction. But both of these are illustrated as problems of understanding in the talk I gave today.
If nobody else is asking questions, probably I'd better give this one.
So Andy, do you want to give you a question?
Yeah, thanks. This is actually kind of follows nicely from Yoshi. So I
you
was
can
thinking,
read it if it's written.
can you hear me? Can you
I think
hear
you're
me?
muted, Andy.
I am not muted.
Oh, it's
Yeah.
muted
No,
on
I
our
can
side.
hear you.
perhaps.
We'll figure it out.
I can hear you, Andy.
Right. Yeah. So everyone on Zoom can hear me.
Yeah, we can hear you now.
All right. Okay. So yeah. So no, this is a really interesting talk, and I'm going to say things like, so I'm the I teach the main undergrad stats subject for the school. So I've thought a lot about this, and I'm afraid that what I'm going to say here is going to make everyone not want me to teach it anymore. But one of the things that I keep sort of circling around because of this, and because of what the things you were talking about just in answer to Yoshi about how what matters is explanation, that we understand it, that I feel like more and more I'm of the view that we can dispense with a lot of the stats we do, and we just need to get better at drawing pictures of the data, and which doesn't solve all of the problems that you posed. Like, I have no idea what the fuck is going on with Stein's paradox, but like, Simpson's paradox and some of these other issues, like they cease to be as much of a danger if people are robustly plotting their data and looking at it in different ways and so forth. And many times, and especially when you get into models that are like multi-level models or with many complicated interactions, we simply can't even understand them anyways. And so I'm increasingly of the view of like, why do we even have these? And so I guess I was wondering to what extent, you kind of think that's also heretical and problematic, or whether, you've landed in a similar place or what.
Now, I've over the years, I've come increasingly. Well, first I should say that initially I found null hypothesis testing as irrational and bizarre, and I was asked to teach it as a graduate student, and did because I could do the math, but I didn't understand what it meant. It made no sense. Then a few years later, in the early 70s, I started teaching Bayesian statistics, which made a lot more sense. And Bayesian statistics did take a small baby step toward induction, because it theoretically took into account priors, which is your prior knowledge. And I would say, for reasons I won't go into, that's only a baby step, but at least it was taking a step toward induction. And but then I sort of realized that, first of all, Bayesian statistics can be very complicated. I've done recent publications about trying to, elaborate Bayesian statistics in a way that would make it rational, and publish that, but it's complicated. And for the point of view of trying to teach statistics in a way that's understandable, we don't want to add complications. We don't want to talk about esoteric Bayesian complications that almost nobody can understand and work out, especially work out. So I think that ideally, for the purposes of both understanding what the data show and for inferring what might have generated the data, the best thing to do is not to use complicated statistics that we don't understand, not to use complicated analysis of variance or some of the more esoteric things that you see these statisticians publish as special ways to analyze the data that's supposed to give you insights into what's going on. See if you can plot the data in a way that makes it obvious what the data is actually showing. And if you're lucky and you get good, reliable data, and you put some error bars around your data, let's say, distributions across people or something, you can just see the eye test is, the interocular eye test is sufficient to show you what's going on. If the patterns that are produced by the data fit the model you have in mind to explain how the data were generated, that's good, without worrying about some of the quantitative details, perhaps. If the directions of predictions are in the right direction all the time. And if you can find a way to show the data and plot the data or present the data that will show that it's not just a matter of noise, that there's some pattern, some reliable pattern signal in the data that isn't just noise, and you can see what it is, then I think maybe it's nice that you be able to understand what's going on from the way of presenting the data, analyzing the data. Then, because the journals insist that you do some statistics to justify what you did, then we go through this exercise of doing some of these fancy analyses. And the funny thing about doing that is that often those fancy analyses we do are nice when they actually match what the data show, but sometimes they're absurd. In other words, it just is an accident. And the best example I know of this is when people compare models and they say one model is doing better than another because, for example, a BIC score, which is the approximation to a Bayesian Bayes factor analysis, shows a better result than another model. The problem is, of course, that BIC doesn't take into account what it should, which is the correlation structure among the parameters. So that actually, when you see a BIC score, you have no idea which model is better. There's no way to tell. And so this is meaningless. Well, who cares? I mean, you're only putting that BIC score in the article because the journal insists you do something. But it better be that the analysis of the data and the patterns you showed in your figure actually show what's going on, and the BIC score will report as long as it points in the right direction, the direction that we already see in the data. So this is a long-winded way of saying that maybe some of these complicated statistics that we carry out are just an exercise that we're trained to do. And what really matters is understanding what the data show. I don't know if that's any help.
No, that's good. That's where I've landed too. I'm glad I'm not a total heretic. So yeah.
Just adding to that, it feels like either the induction route or the deduction route are reactionary.
Wait, say that again, what?
So, as Andy was saying about the need for just being able to plot the data, right, and show it. To me, that's very much the induction kind of route where you can see the data and you can infer what is going on. And then there's the deduction route, which is very much the statistics and going down into the math and trying to make some kind of deduction about what the data show. But it feels to me that these are reactionary in response to the meta-scientific debates that are ongoing. So we have a replication crisis, and then we go into this hardcore, everything has to be set, stats. And then we get to a stage where we are now, where we go, we've gone too far. We need to make it so that it's actually, explainable, because we're losing understanding in the data. I feel like, is this just a cycle that we're going through, and that we've always been going through in science?
This comes down to, in part, what I keep saying all the time and have been saying for many years: science is hard. And there's no easy answers. And the induction especially is particularly hard in trying to understand what data mean and the best account for the data. And it's easy to get it wrong. And when I say, oh, let's plot the data and make it clear what's happening, that itself is hard, because the way you plot the data and the way you show what's happening is itself an art. It's a matter of what you choose to show and what you chose to highlight and the way you plot it and so on. This is all very difficult. So though ideally, yes, we should show what's happening in the data with figures and with analyses that are make it clear. But how do we do that? That itself is something that requires a good deal of scientific judgment. So there's no easy answer. And the question you have about, are we going through a cycle maybe of maybe we've gone too far with all these fancy statistics that the statisticians have done? Well, the problem with some of these fancy analyses, statistical analyses that we constantly see being published all the time, is that maybe the person who proposes the analysis understands it. There's a question whether that's true, but or understands it at what level might be the right answer. They might understand it at a deduction level. It's not always clear that they understand it at a level of induction. But even if they do, I doubt any of the people who would ever use it would understand it unless they spent a few years like the original statistician working through the fancy statistics. So there's a question there about what's the point? Why use some fancy statistical analyses because somebody else has proposed it if you don't understand it? I mean, that's a good question. But this all raises the pedagogical question, which I asked in the first place, which is, what do we aim for here? What level of understanding can we expect if we're teaching statistics? Most of you will, many of you will. Undergraduates, graduates, or anything else, what level of understanding should we aim for and how? I don't know the answer to this. I mean, Goldstone, for example, studies educational questions and and looks at statistics and so on, and hopes to impart certain levels of understanding. When I raised this issues with him recently, he didn't have any easy answers either. In other words, I don't know the answer of how to do this. All I know is it's hard, and I don't think there's any easy answers. But we do hope to teach, and we hope that the people we're teaching will learn something useful and take from the courses we teach. And if it's this difficult to get across even the simplest statistical notions in a way that is clear, then what should we aim for? I don't know the answer to this. I'm not an educational psychologist, and I'm just amused by the question. I don't know what the answer is. Do any of you have answers? I'd like to hear them.
So I think we might stop there. Since that was pretty much rhetorical. So if anyone wants to stay around, we do have the room booked for another half hour. So if you want to stay and ask any additional questions, that's fine. Otherwise, we will be taking Rich out for lunch, and everyone's welcome to come with us, but it's not on the CHDH this time around. So, but everybody's welcome nonetheless. Okay, thanks very much, Rich.